Okay, great. So I guess everything's working fine, right, Hassan? Let's start.
Yes, I can confirm that you are live on YouTube.
Okay, great, thanks. So welcome everyone. This is the sixth meeting or PNS Ramulator class. And today I'm going to cover the DAMOV paper, which is tied to processing memory, not necessarily Ramulator, but Ramulator was used as a base for all of the experiments that we did in this work. So is, let's say, extension of Ramulator per se. So the title of this work is DAMOV, a new methodology and benchmark suite for evaluating data movement bottlenecks, and it was published in IEEE Access last year. So let's get started with this talk with the executive summary. So the problem that this paper is trying to solve is that even though data movement is a major bottleneck in today's systems, it is still unclear to us how we can identify different sources of data movement bottlenecks in application and the most suitable mitigation technique, let's say caching, prefetching, or data processing for a particular data movement bottleneck. Therefore, the goal of this work is twofold. First, you want to design a methodology to identify sources of data movement bottlenecks, and second, to compare compute and memory-centric data movement mitigation techniques to identify which data movement mitigation technique is the best for a particular application. The key approach that we take in this project is to perform a large-scale application characterization, so we can identify key metrics that can review the sources of data movement bottleneck in application. We have four main contributions in this work. First, we do large-scale experimental characterization of 77,000 functions across 345 application domains, applications from different domains. Based on this experimental characterization, we develop a new methodology that can be used to classify the applications in 6 different classes of data movement bottlenecks, and also their relationship with different data movement mitigation techniques. Third, we apply this methodology to this large number of functions, and then we collect them into a benchmark suite, which is called DAMOV, which has 144 functions classified into those 6 different classes of data movement bottlenecks. Then we use DAMOV in 4 case studies to highlight how it can be applicable to open research problems, particularly on on processing memory. So DAMOV is open source and is available in this link from our Safari GitHub. So this is the outline for this talk. So first, I'm going to briefly talk about data movement bottlenecks. Second, I'm going to cover our methodology, and then the 3 steps of our methodology into details, and then finally talk about our case studies. Feel free to ask any question in the YouTube chat. I'm going to try to collect them as we go. So let's get started with data movement bottlenecks. So data movement has become a major bottleneck in today's systems, and it happened for at least 3 reasons. So first, if application does not have enough data locality, this application is not going to make effective use of the cache hierarchy. Second, if the DRAM system cannot provide enough memory bandwidth for the application. And third, caused by the high average access memory time incur in application that does need to access the whole memory hierarchy. High-performance computer systems have evolved to include many techniques in the CPU core that can be used to mitigate data movement bottlenecks for a particular application, those including deep cache hierarchies or aggressive hardware prefetchers. And we refer to those mechanisms as compute-centric data movement mitigation techniques or compute-centric architectures. However, such mechanisms not only come with large costs in terms of area and complexity, but they also fail to mitigate data movement bottlenecks for many emerging applications. One emerging technique that aims to alleviate data movement bottlenecks in emerging applications is what we call memory-centric architectures. In such architectures, the cost of data movement is reduced by placing computation capabilities close to memory. Near data processing, or NDP, as we're going to mention in this presentation, is a good example of a memory-centric architecture. In an NDP system, the logic close to memory has access to data in the main memory with high bandwidth and shorter average memory access time, which can benefit memory-bound applications. Therefore, the goal of new data processing is mainly to mitigate data movement bottlenecks. New data processing is not a new idea. In fact, there are new data processing architectures being proposed from the early 70s, so 5 decades from now. However, only recently the industry have started catching up with the first commercially available new data processing architectures. Here, I'm going to highlight 2 of those commercially available new data processing architecture. But since this presentation, many more have been proposed, which I'm going to briefly talk about. So the first one is the UpMem architecture designed by a company of same name, proposed in 2019. And it's pretty much is a new DRAM bank processing system for general purpose computing. The proposed architecture can reach a peak compute throughput of 0.9 tera operations per second. The second one is the Samsung Film DRAM. It's similar to the UpMem architecture in the sense that it also adds the computing logic nearby DRAM banks, but here it targets mainly neural networks. And this architecture can achieve 1.2 teraflops per second of compute throughput. After those proposals, Samsung have released also another data processing architecture different from this Film DRAM one. Alibaba also have proposed one, and also SK Hynix. So it's becoming a trend across memory manufacturers to propose the data processing targeting memory-intensive workloads. So when should we employ the data processing? So as I said, as I just showed here, there have been different data processing architectures being proposed for general purpose computing or neural networks, but there are many proposals particularly from academia, that propose new data processing for varying application domains, like for example, graph processing, mobile consumer workloads, neural networks, DNA sequence mapping, databases, time series analysis, and many more. All those works rely on different methodologies to identify memory bottlenecks in a system. And often such methodologies are intuitively used to indicate if application would benefit for NDP or not. However, as I'm going to show next, none of those models are comprehensively enough to identify memory bottlenecks or NDP suitability across a large number of applications. This happens because those models are not built targeted to identify specific sources of data movement bottlenecks, and often their definitions of compute or memory bound are not enough to identify new data process suitability. For that, we are going to analyze 2 commonly used approaches. The first one is what we call the roofline model, which correlates arithmetic intensity with performance. And second is identifying applications with high misses per kilo instructions. That's the vocation misses per kilo instructions. So first, I get started with the roofline model. So the roofline model is a simple model used to identify if application is memory bound or compute bound. The x-axis of this plot here in the roofline model show the arithmetic intensity in operations per second, and while the y-axis show the performance of the system in giga operations per second. It has 2 main lines that characterize the application in this system. So the first line is called the compute roof, and is defined as the maximum peak system throughput. Applications below this curve are called compute bound, and prior works have shown that these compute bound applications do not benefit from the data processing. The second line here is called the memory roof. It is defined as the maximum bandwidth, DRAM bandwidth of the system times the arithmetic intensity of our application. And prior works have shown that applications that lies below this memory roof can benefit from any data processing. So we use this model to characterize more than 4 applications that we are going to analyze next, and we compare such the benefits of a CPU-based system or a compute-centric system over any data processing architecture. So in this plot here, we classify applications in 4 main categories. So the applications that run faster on the CPU compared to running on the NDP system, run faster on the NDP compared to running the CPU, have similar performance on the CPU and in the NDP system, and the performance depends on the particular system configurations, as for example, the core count. Based on that, we draw the following observations. So first, as prior works have suggested, memory-bound applications do benefit from the data processing. Likewise, compute-bound applications also do not benefit from data processing and often run faster on the CPU. However, we also observe that some memory-bound applications can also not benefit from the data processing or benefit from data processing in a particular configurations, for example, for different number of cores. This behavior also happens for compute-bound applications. Therefore, we conclude that the roofline model cannot currently account for NDP suitability of a variety number of memory-bound functions. Next, we analyze another metric used to indicate if application can benefit from data processing. Prior works have shown that applications with high less-level cache misses per kilo instructions, usually a value higher than 10, benefit from MDP. We check this observation by evaluating the speedup providing the NDP system for a large number of applications here in the y-axis, and the application PKI here in the x-axis. We make the following observations. First, as expected, applications with high less-level misses per kilo instructions always benefit from NDP. Likewise, applications with low MPKI never benefit from MDP. However, we found a group of applications with low MPKI which can either benefit from NDP based on a particular system configuration, or they can have similar performance both in the NDP system and in the CPU-based system. Therefore, we conclude that the less-level cache MPKI by itself cannot currently account for NDP suitability. So, to summarize our analysis, different approaches have been used by prior works to identify memory bottlenecks and NDP suitability for a particular application. However, we observe that such methodologies are not comprehensively enough to identify and characterize different data movement bottlenecks in a particular application and correlate these data movement bottlenecks with the most suitable data movement mitigation mechanism. Therefore, our goal is this work is to develop a methodology that can identify sources of data movement bottlenecks in a methodical way, and also can compare compute and memory-centric data movement mitigation techniques comprehensively across a large number of applications. Next, I will give an overview of our workload characterization methodology. We developed a new workload characterization methodology to analyze data movement bottlenecks and suitability of different data movement mitigation techniques for a particular class of data movement bottleneck. To do that, we use two main profiling strategies. The first one is architecture-independent profiling tools, which provides metrics that can characterize the application memory behavior independently on the underlying hardware. Also, we use architecture-dependent profiling tools, which can evaluate the impact of the system configuration, as for example, the cache hierarchy, on the memory behavior. Our methodology has three main steps. It takes as input application source code and its input dataset. And then in step one, we use a hardware profiling tool to identify memory-bound functions across many applications. This step allows us for a quick first-level identification of many applications that suffer from memory bottlenecks and functions within these applications that causes those memory bottlenecks. Then we utilize a new simulator called DAMOV sim to collect key metrics that can and performance of applications, which are going to be used in the next two steps. In step two, we used architecture-independent profiling tools to collect metrics that provide insights about the memory access behavior of the memory-bounded functions, while in step three, we collect architecture-dependent metrics to and the performance and energy of the application when each of our three candidate data movement mitigation mechanisms are applied to the system. By combining all of this data from step 1, 2, and 3, we classify the application into 6 different classes of data movement bottleneck, and also how the different data movement mitigation techniques can mitigate the bottlenecks for those applications. So let's check the first step first. The goal of our first step is to identify functions from an application that suffer from data movement bottlenecks. To profile the application identifying functions that suffer from data movement bottlenecks, we use a hardware profiling tool. In this work, we use the Intel VTune profiling tool, which provides a metric called memory bound, which is defined as the percentage of CPU pipeline slots that are not utilized because of memory stalls. Let's now look at the second step. In step 2, we will aim to analyze the application memory characteristics as locality, thus we can understand how it affects the components of the memory system, as for example, cache behavior or prefetching. To this end, we evaluate 2 key metrics. We first evaluate special locality from application. For this, we collect the memory trace of application to build a histogram called the stride profile, where each bin stores how many times each stride appears in the memory trace. In this example here, the stride between the first access address and the next access address is equal to 1. We increment the stride profile histogram in bin 1 to indicate such a stride has been observed. Use the stride profile histogram to calculate the cumulative distribution of stride profiles, which represents the final spatial locality value. Application with spatial locality close to 0 is caused by a large stride values or random access, as shown in this example. In such case, we say that the application has low spatial locality. A spatial locality value close to 1 is caused by a completely sequential access pattern. In such case, we say the application has high spatial locality. Similarly, we evaluate how much temporal locality application has. For this, we collect the memory trace of application to create a histogram called reuse profile, where each bin represents the number of times a memory address is reused. For each memory address, we increment the bin that represents the corresponding number of repetitions. This example here, memory address A is reused 4 times. Thus, we increment the reuse profile histogram in bin 4 to indicate that such reuse has been observed. We use the reuse profile histogram to calculate the cumulative distribution of reuse profiles, which represents the final temporal locality value. A temporal locality value close to 0 is caused by low data reuse. In such case, we say the application has low temporal locality. A temporal locality value close to 1 is caused by high data reuse, and in such case, we say the application has high temporal locality. Finally, let's check the step 3 of our methodology. While step 2 allows us to understand inherent application sources of memory bottlenecks, it's important to understand how hardware architecture features can also result in memory bottlenecks. As a result, in our third step, we perform a scalability analysis of the function selected in step 1, where we evaluate performance and energy scaling for 3 different system configurations. The scalability analysis makes use of 3 architecture-independent metrics. First, arithmetic intensity, or AI, which is defined as the number of arithmetic and logic operations performed per L1 cache line access. This metric indicates how much computation there is per memory request. Intuitively, applications with higher arithmetic intensity are likely to be computationally intensive, while applications with lower arithmetic intensity tends to be more memory intensive. Second, we use the less level cache misses per kilo instructions, defined as the number of less level cache misses per 1,000 instructions. This metric is considered to be a good indication of NDP suitability by several prior works, since it indicates memory intensity of application. And third, we design a new metric called last to first miss ratio, or LFMR, defined as the ratio between the number of less level cache misses and the total number of L1 cache misses. We find that this metric accurately identifying how much application benefits from the cache hierarchy, and last to first miss ratio value close to 0 means that the number of less level cache misses is very small compared to the number of L1 misses. However, a less level LFMR value close to 1 means that very few L1 misses hit in L2 and L3 caches, and the application does not benefit much from a deep cache hierarchy. So then we perform our scalability analysis. The goal of scalability analysis is to nail down the specific sources of data movement bottleneck in an application. In this analysis, we evaluate the performance and energy scaling of application in 3 different system configurations and collect the key metrics for bottleneck classification. During the scalability analysis, we simulate 3 system configurations of our general purpose multi-core processor. To this end, we build a framework that integrates ZSIM CPU simulator with Ramulator memory simulator to produce a fast, scalable, and cycle-accurate simulator, which is called the DAMOV sim. We use ZSIM to simulate the core microarchitecture, cache hierarchy, coherency protocol, and prefetchers, while we use Ramulator to simulate the DRAM architecture, memory controller, and memory access. The first configuration that we evaluate is of a whole CPU with a deep cache hierarchy, with a 32 kilobyte private L1 cache, 256 kilobytes private L2 cache, and a shared 8 megabytes L3 cache. The second configuration is of an NDP system with only a private read-only L1 cache of 32 kilobytes. In our paper, we evaluate a third configuration where we kept the same system configuration as configuration 1, but to include a hardware prefetcher. It's important to say that the remaining components of the processor configuration across all of those three different configurations are kept the same. So we can isolate the impact only on the cache, prefetchers, and NDP on application performance and energy consumption. And this way, we can isolate the data movement bottleneck or data movement requirement for a particular workload. For all configurations, we doing our scalability analysis, we change the number of cores or evaluate the number of cores in our analysis from 1 to 256. As prior works have shown that large core counts are required to saturate the high bandwidth available in 3D stack memories, and because CPUs and NDP proposals can have varying core counts. We simulate a memory hierarchy similar to that of the hybrid memory cube or HMC memory, where the whole CPU access memory through a high speed off-chip link, and and the NDP system has access to memory inside the logic layer of the 3D stack memory, which provides the CPU core in the NDP system with higher bandwidth and lower memory access latency. Next, we apply our three-step methodology to characterize the sources of memory bottlenecks across a large number of applications. So in this work, we analyzed 345 applications for varying domains, those being graph processing, deep neural networks, physics, high-performance computing, genomics, and many more. We observed that applications that benefit from MDP and suffer from memory bottlenecks have a memory bound metric greater than 30% and takes at least 3% of the clock cycles of the total application. Based on this, we obtain 144 functions from a total of 77,000 functions that we analyzed, and we select 44 functions to apply step 2 and step 3 of our methodology, and the 100 left functions so we can do the validation of our methodology later on. Next, we apply step 2 of our methodology to the selected 44 application functions. So we collect spatial and temporal locality metrics from the selected 44 application functions and perform a locality-based clustering. So we use the k-means cluster algorithm to create two groups of applications: applications with low locality here in orange and applications with high locality here in blue. The closer a benchmark is to the bottom left corner of the plot, in other words, the lower the temporal and spatial locality it displays, the less likely is going to take advantage of a deep cache hierarchy and prefetchers. With this cluster in mind, we conduct of bottleneck analysis in step 3. So with the two groups of functions we identify in step 2, we use three key metrics from step 3, which are less to first miss ratio and PKI and arithmetic intensity, plus temporal locality from step 2 to classify the memory bottlenecks of applications, which we found 6 different classes of memory bottlenecks based on these metric values. These classes of memory bottlenecks are DRAM bandwidth bound applications, DRAM latency bound applications, applications that are bound by L1 and L2 cache capacity, applications that are bound by L3 cache contention, L1 cache capacity bound applications, and compute bound applications. With such classification, we analyze how these functions benefit or correlate with different data movement mitigation mechanisms in terms of performance and energy using our scalability analysis. Next, we look into details about the scalability analysis of DRAM bandwidth bound applications. Applications in this class have low temporal locality, high left to first miss ratio, high PKI, and lower arithmetic intensity. We make the following observations. First, applications in this class exert high memory pressure in the memory system. It means that they will likely require high memory bandwidth from the memory system. And to understand how such high memory pressure demand impacts performance, we observe how the performance scales while increasing the number of cores. As we can see here in the figure, the host performance scales well until the memory bottleneck saturates at 64 cores. The performance of NDP system, on the other hand, scales much better due to the large available bandwidth within the memory, the 3D stack memory chip. Therefore, we conclude that DRAM bandwidth bound applications highly benefit from NDP architectures because they take advantage of the high memory bandwidth available within the memory device. Likewise, we also analyze the energy consumption of the DRAM bandwidth bound applications when executing the whole CPU system and in the NDP system. As mentioned before, applications in class 1A have higher less first miss ratio, which means that they do not make effective use of L2 and L3 caches. We observe how much inefficiency impacts energy consumption for the whole CPU and NDP system. First, as we can see in the figure, the host energy consumption is dominated by L3 cache lookups and high energy consumption of cheap DRAM requests, as expected due to the large less first miss ratio. Second, on the other hand, NDP reduces energy consumption compared to the host CPU since it avoids such L3 cache lookups and also the off-chip memory traffic. Therefore, we conclude that DRAM bandwidth bound applications highly benefit from NDP architectures when consider energy consumption, since the NDP system does not access L2 and L3 and off-chip links, leading to large system energy reduction. Now we analyze DRAM latency bound applications. Applications in this class have low temporal locality, high less first miss ratio, low MPKI, and low arithmetic intensity. Applications in class 1B do not make effective use of the cache hierarchy, differently from applications in class 1A, since they have, while they still have high less first miss ratio, indicating that they do not make effective good use of the L2 and L3 caches. We observe that even though the host performance scales well, the NDP performance is always larger than the host performance. We find that the NDP improves performance because it also reduces average memory access time. Memory access time takes longer in the CPU system than in the NDP system due to the additional latency of looking up requests in the L2 and L3 caches, even though data is rarely present in those caches and going through the off-chip links and DRAM. To conclude, class 1B functions benefit from NDP systems, but primarily because of its lower memory access latency provided by the NDP system. These functions could also benefit from other latency reduction and energy reduction, memory reduction techniques, such as L2 and L3 cache bypassing and lower latency DRAM systems. Now we analyze L1 and L2 cache capacity bound applications. Applications in this class have low temporal locality, decreasing less first miss ratio when we increase the number of cores, low MPKI, and lower arithmetic intensity. We find that the behavior of the function in this class depends on the number of cores the system uses. The decreasing less first miss ratio indicates that L2 and L3 caches become efficient when increasing the core count. We analyze how this impacts performance. At low core count, the NDP system outperforms the host CPU system. With a low number of cores, the application have medium to high less first miss ratio and behave like class 1B functions, where they are DRAM latency bound. However, as the core count increases, the host CPU system begins to outperform the NDP system. This is because as the core count increases, the aggregate L1 and L2 cache size available at the host CPU system also increases, which reduces the miss rate of both L2 and L3 caches. To conclude, we find that the primary source of memory bottleneck in class 1C functions is the limit L1 and L2 cache capacity. Therefore, while the NDP system improves performance at low core counts, the NDP system does not provide performance benefits across all core counts from class 1C functions. Next, we analyze applications that are bottlenecked by L3 cache contention. Applications in this class have high temporal locality, increasing less first miss ratio with the number of cores, low MPKI, and low arithmetic intensity. The decreasing less first miss ratio indicates that L2 and L3 caches turn inefficient as we increase the number of cores. We observe that such inefficiency impacts host NDP performance. And low core counts, the functions do not benefit from NDP system. This is because at low core counts, these functions make reasonable good use of the cache hierarchy. At high core counts, the host CPU performance starts to decrease, and being outperformed by the NDP cores. This is because class 2A functions are bottlenecked by cache contention. At high core counts, this contention reduces the cache effectiveness and causes the less first miss ratio to increase near to 1. Thus, increase the number of memory requests that the application needs to be served by DRAM. With the less level cache becoming essentially ineffective, the NDP system greatly improved performance over the CPU system. We conclude that applications in this class are bottlenecked by cache contention. At high core counts, those high locality applications become DRAM latency bound. Next, we analyze applications bottlenecked by L1 and L2 cache capacity. Applications in this class have high temporal locality, low last first miss ratio, low MPKI, and low arithmetic intensity. The low last first miss ratio and MPKI and high temporal locality indicate the applications in this class make effective use of the cache hierarchy and also have low memory intensity. Also, the low arithmetic intensity for such applications indicates that they execute few operations per byte loaded from the memory hierarchy. You observe that the host performance and the NDP performance scale is in a similar fashion, even though the NDP system has less on-chip SRAM area for the caches. Such reduction of SRAM size does not hurt performance of the NDP system, since the L1 cache present in both host and NDP systems dominates the average memory access time for such applications. We conclude that even though the NDP system does not mitigate any memory bottleneck for these applications, it can still be used to reduce overall SRAM area. Finally, we analyze compute-bound applications. Applications in this class have high temporal locality, low last first miss ratio, low MPKI, and high arithmetic intensity. The low last first miss ratio MPKI and high temporal locality of these applications indicate that they make good use of the cache hierarchy. However, contrary to class 2B applications, the high arithmetic intensity of these applications indicate that they execute many operations per byte loaded from the memory hierarchy. You observe that the host performance is always greater than the DP performance for the application in this class. We conclude that class 2C functions do not experience large memory bottlenecks and are not a good fit for NDP systems in terms of performance. To conclude, our scalability analysis led us to 6 distinct classes of memory bottlenecks, which correlate to different data movement mitigation mechanisms. We invite you to check our paper for a comprehensive discussion about the performance and energy scalability for each one of those memory bottleneck classes. Next, we aim to evaluate the accuracy of our workload characterization on a large set of functions. To this end, we apply step 2 and step 3 of our methodology to the remaining 100 memory-bound functions we obtain in step 1. Then, we perform a two-phase validation to calculate the accuracy of our workload characterization. In phase 1 of our validation, we calculate the threshold values that we use to define the low-high boundaries for each one of the 4 metrics used to cluster the initial 44 applications in the 6 different classes of memory bottlenecks. We also include the last first miss ratio curve slope to indicate if the last first miss ratio increases, decreases, or stays constant as we increase the number of cores. In phase 2 of our validation, we calculate the accuracy of our workload characterization by classifying the remaining 100 memory-bound functions using the threshold values obtained from phase 1 and the last first miss ratio curve slope. After phase 2, a function is considered to be currently classified into a correct memory bottleneck class if it fits the definition of the assigned class using the threshold values obtained in phase 1 and follows the expected performance trends of the assigned class when the function is executed in the host CPU system and in the NDP system. By applying this such validation methodology, you find that we can currently classify 97% of the 100 memory-bound functions into one of those 6 memory bottleneck classes that we previously showed. We expect that the accuracy of our methodology can be further improved by incorporating more workloads into our workload suite and fine-tuning each metric that encompass an even larger set of applications. We invite you to check our paper for further analysis and discussions, including the effective of less level cache size in our classification, which you observe that large L3 cache size, for example, 512 megabytes L3 cache sizes can mitigate some cache contention issues, but not all. A summary of workload methodology, including workload characterization, using in other hosts and DP cores, the limitations of our methodology, and benchmark diversity of DAMOV. All of this is available in our paper. Finally, I will briefly talk about the case studies we use in this work. There are still many open research problems related to NDP system design, including, for example, how to design good interconnects, data mapping allocation mechanisms for NDP system applications, how to design efficient NDP core designs, those being either accelerator or general purpose cores, the ideal of load granularity for NDP application, how to program NDP cores, how to maintain coherence, how to do system integration, and many more. The goal of these case studies that we are going to show next is to demonstrate how DAMOV can be useful to study those open NDP system design challenges or questions. We present 4 case studies. In the first case study, we use DAMOV to evaluate the interconnection network overheads that NDP cores placed in different vaults of a 3D stack memory suffers from. We observed that a large portion of the memory requests NDP core issues go to remote vaults, which increases the memory access latency for NDP cores. We believe that DAMOV can be employed to study better data mapping techniques and interconnection network designs that aim to minimize the number of remote memory access the NDP core execute and the interconnect network latency overheads. In the second case study, we evaluate the benefits that NDP accelerators can provide for 3 applications from a benchmark suite. We compare the performance improvements an NDP accelerator provides against the compute-centric version of the same accelerator. We observe that the NDP accelerator provides significant performance benefits compared to the compute-centric version of the same accelerator for applications in class 1A and 1B. At the same time, it does not improve performance for applications in class 2C. We believe that DAMOV can aid the design of NDP accelerators that target different memory bottlenecks in the system. In the third case study, we perform an ISO area and power performance evaluation to compare NDP systems using in-order and out-of-order cores. We observe that in-order cores performance benefits for applications are limited by the core's static structure and scheduling mechanism. We believe that better NDP systems can be built by leveraging techniques that enable dynamic structure and scheduling without incurring the large area and power overhead or out-of-order cores. DAMOV can help in this analysis and development of such NDP architectures. In the fourth case study, we evaluate the benefits of offloading small portions of code, for example, a basic block, to NDP, which simplifies the design of the NDP system. We observe that for many applications, a small portion of basic block is responsible for most of the less level cache misses. By offloading these basic blocks to an NDP core, we observe a performance improvement of 1.2 times compared to the whole CPU system. We believe that DAMOV can be used to identify simple NDP instructions that enable building efficient NDP systems in the future. So for more details on all of those case studies, we invite you to check our paper. In this talk, I'm going to dig a little bit deeper into the NDP accelerator case study. So the goal of this case study, as I said previously, is to evaluate compute-centric versus NDPs or memory-centric accelerators. To do that, we design tailored accelerators for each one of the applications, for 3 applications from a benchmark suite. And then we design compute-centric accelerator, where the custom accelerator accesses main memory through off-chip links, similar to the traditional host CPU systems. And an NDP accelerator, where the custom accelerator accesses the memory device or the DRAM device through internally from within a 3D stack chip, which again provides higher bandwidth and a shorter memory access latency. Then we compare the performance those 2 accelerators can provide for 3 different applications from our benchmark suite. So first, we take applications from class 1A. Those are DRAM benefit bound applications, and one application from class 1B, which are memory DRAM latency bound applications, an application from class 2C, which are compute bound applications. And we compare the speed up, the y-axis here, of the compute-centric accelerator, speed up over the compute-centric accelerator. So we observe that the application class 1A highly benefit for the NDP accelerator, likewise from the application in class 1B, while the application in class 2C does not benefit from the NDP accelerator at all. Therefore, we conclude that the performance of the NDP accelerators are in line with the characteristics of the memory bottleneck classes that we previously identified. And also, it's important to say that our memory bottleneck classification can be applied to study other type of system configurations other than the general proposed cores that we use in our paper, as we demonstrate here in this case study. Again, there are much more details in each one of those case studies in our paper, which we invite you to check. So we open source DAMOV to facilitate further research into mitigating data movement bottleneck, including the data processing. So in our DAMOV repository, we provide the complete set of 144 application functions that compose our benchmark suite and the DAMOV simulator. And we can get this into the Simu Safari GitHub repository. To conclude, the problem that this paper is trying to solve is that even though we know that data movement is a major bottleneck in today's systems, it's still unclear how we can identify different sources of data movement bottlenecks from application and the most suitable data movement mitigation technique for a particular data movement bottleneck. The goal of this work then is twofold. First, design a methodology that can identify sources of data movement bottlenecks, and second, to compare compute memory-centric data movement mitigation techniques. The key approach that we take is to perform a large-scale application characterization to identify key metrics that can reveal the sources of data movement bottlenecks. We have four main contributions of this work. In this work, first, we perform a large-scale application characterization of over 77,000 functions across 345 applications for varying application domains. Based on that, we develop a three-step methodology that can characterize the application in 6 different classes of data movement bottlenecks and their relationship with different data movement mitigation techniques. From which we develop a new benchmark suite called DAMOV, which target the study of data movement bottlenecks in a system. Then we highlight the benefit of our benchmark suite for 4 case studies to highlight DAMOV's applicability to open research problems or new data processing. Again, DAMOV is freely open source in our GitHub repository. So thanks a lot for listening, and I'm going to check if we have any question on the YouTube chat. See. I guess there is no question. So thanks a lot for listening. If you have any question about the move, feel free to fire me an email. I'll be glad to take them. So I think we are done for today. Thanks a lot.